Okay, is recording on? Recording looks like it's on. I'm going to go ahead and share my screen. We have a lot to talk about today. So this week, you guys are laser cutting, right? Some of you are probably laser cutting today. Some of you might have already even started laser cutting. There might be someone that's laser cutting right now and not even logged into class because of it. That's fine. That's my hope anyway, because we need to use up all those slots. The sooner you guys laser cut your rib system, I gave you that Rhino script. It should be relatively easy. This week we're going to start looking at the components that can populate the grid shell. All right. So again, the ribs are like a structural two-way system, right? But then the sort of skin of the building, or the skin of this grid shell, I would argue, could be populated with some sort of shading component. And next week we'll work up, after you've started designing your shading component this week, next week we'll start to talk about performance criteria by which you can begin to adjust it. But so this week, that's what we're talking about, these shading components, how you can begin to populate your surface, your grid shell surface with a set of differentiated components that work together as a system, but individually can be unique based off of whatever criteria you're using to generate the parameters for it. So today we'll talk about that in class. We'll do an in-class demonstration. Once that demonstration is over, I'll go ahead and upload that to YouTube, and it'll be right here in Canvas, where this little pink selection box is. For Wednesday, you need to start designing your shading component. And so what I recommend is before you even start screwing around in Rhino or Grasshopper, you just make a quick sketch. This obviously is a pretty quick sketch. It took me like 2 seconds to do right before class, actually. Start by making a quick sketch of your intentions along with the needed geometric ingredients and parameters, right? So in this case, I drew, if I'm zooming into one of these cells on my surface, right? Let's say that here's an isoparm, an isoparm, isoparm, an isoparm. I look at one of those checkers, right? Like you guys generated in video 20, which I'll go back over again today, where you divide a surface up into smaller components, smaller checkers. Then I have vertices for each of these quads, right? So vertex 1, vertex 2, vertex 3, vertex 4. Those are points that I'm going to use. Again, this is where everything starts to come together. So everything that we're doing with surfaces also comes full circle and works with all the stuff that we did with points and lines and curves before, right? Because what we're doing is we're identifying parts of the surface, and locations on the surface are identified with points, right? So we have vertices. We have, let's say, a point on the surface, right, which we can evaluate the surface at a UV parameter. We give it a U location and a V location, and then at that moment where those latitude and longitude lines intersect, that's a point that it gives us, right? We can generate lots of different lines and points based off of the geometry that we have here in order to create more surfaces. And so the example I'm giving today, this is just a quick sketch of that, right? So what I'm going to do is I'm going to find the vertices for each of these checkers on my larger checkerboard of the surface. Vertice 1, vertice 2, vertice 3, vertice 4, vertice 4. I'll actually place a point along the surface, in this case at the midpoint, let's say U and V parameter of 0.5 and 0.5. While I'm evaluating the surface at that location, it'll also give me the other properties of the surface, like the normal direction, right? Sort of direction perpendicular to the curvature of the surface at that location. And I can actually use that and draw a line upwards, right? By start point direction and length, and find an endpoint up here. That would be the apex for a pyramid. Then I can start to draw 2, 3, or 4 sides of the pyramid, right? By simply connecting a vertex 1, vertex 2 in the apex point, vertex 2, vertex 3 in the apex point, and start making triangular surfaces to create, in this case, what'll look like a cheese grater sort of geometry. Okay, so that's where we're going. That's what I mean by a sketch. I usually just sort of grab a piece of paper or a napkin or something nearby and sort of figure out what I'm going to do and think maybe a couple steps ahead before I start screwing around inside of Grasshopper for anything and remotely sophisticated. I find it's actually helpful just to sort of draw something out really quickly. So between now and Wednesday, you need to start designing. I recommend this first step, just simply doing a quick sketch before you start to dig into Grasshopper and Rhino. I also included this video 20, which we'll be going over today, but I just included it here in case you need to refer back to it, right? So this was one of the last videos you watched when we started Project 2, when you had a set of demonstration videos to watch, right? You take a larger surface and you break it up into a little, into grid cells, right? Almost like a spreadsheet. You have columns and rows, and we did stuff with some of the points and things like that. So that's there in case you need it. And then this last video, where we join, unroll, and label these components once they're created, right, into a grid. So I've included this as a video demonstration. Okay, we'll also be going over today and Wednesday this week in person. And I've also included the grasshopper graph for this example here in case you need to refer back to it, okay, and see what's going on. Sometimes that's helpful. Just sort of look at it and play around with the slide bars and stuff. Okay, now I kind of understand what's going on. Okay, I see. You know, and I can, you know, this is a way to see what's going on without hearing my voice. Sometimes, you know, you probably appreciate that, I'm sure. All right. So let's see. Yeah, anyway, so between today and Wednesday, I want to sort of give you a better sense of the timeline because it seems like that may be a point of confusion, right? This week, you're laser cutting the first prototype of your ribs for your grid shell, right? You should already have had that done over the weekend. You've signed up for a time. It's a matter of just showing up at the right time at the right place with your materials, right? This week. But in addition to just doing that, right, because that takes half an hour of your time, in class, we'll be talking about creating these unique shading components. Between now and Wednesday, you need to start this process, start designing again, start with a sketch, then start to work through the grasshopper stuff. I would also request that you just watch this joining, unrolling, labeling, B-reps stuff, right? It sort of spans between some of the stuff we're going to talk about today and some of the stuff we're going to talk about on Wednesday, right? But between today all the way this week and up until next Monday, right? The goal is for you to create your own sort of robust shading component, right? That can be that populates your surface, okay? And then on next Monday, I'll give you a graph and we can start talking about measuring for performance, okay? So that means that between now and Wednesday, I expect you to just sort of like immerse yourself into this stuff. I'm gonna throw a lot at you in the in-class demonstrations as well as the videos that I'm giving you and the example files that I'm giving you, okay? But ultimately, between now over this next week until next Monday, your goal is to design and instantiate, right, your own shading component. And I say your own shading component because I'm going to show you a really simple version of a shading component like this one, right? Where it's like two triangles, so like half of a pyramid, basically populating each of these cells. You're not allowed to do that one because it's so simple, and I just showed you how, right? So and frankly, that's like the bare minimum, right? And so it's up to you, and again, it doesn't have to be really complicated at all, okay? But it's up to you to create your own. That's not the one I just showed you, okay? And there, you know, honestly, there will be more than one of the same type. Like you guys, there's only a limited number of things you can do. But I can show you some examples of what others did in the past as well. So, all right. Last but not least, when it comes to unrolling these things, let's say I'm working with a bunch of triangles and things like that. What's unique about a triangle as opposed to a quad? Anybody want to guess? When it comes to sort of laying things out for fabrication with a laser cutter. Why do I like triangles a lot when it comes to using the laser cutter? Well, the laser cutter, just as a hint, right? The laser cutter only cuts things that can be flattened out in a plane, right? So what's unique about a triangle? Every single triangle is planar. Every single one, right? Basically you can draw a plane through any 3 points in space, right? So if you're dealing with triangular surfaces, then you're guaranteed to have, you know, something that's planar and can be unrolled or unfolded back onto the XY plane without it ripping, tearing, or stretching, okay? All right, so let me just find the right, Sorry, I just got to find the right window here. I thought I had it up. Maybe I don't have it up yet. I will though. All right. Just pull up this PowerPoint really quickly. I don't know why it closed. That doesn't bode well for the rest of the day. My computer keeps shutting things down unexpectedly. Okay. So not to bore you guys to death, but can you see this PowerPoint? It says digital fabrication, planar fabrication. Okay, great. So we're talking about three-dimensional items, how to begin to take that logic and break them down into a bunch of two-dimensional components that can be much more easily made and fabricated, and then reassembled back into three-dimensional assembly, right? So much like we were doing with the grid shell already, but I just wanted to sort of talk about some of these techniques and how they relate to some of the tools that you can use in Rhino and Grasshopper, of course. To a certain extent, Autodesk tools, mainly Slicer. I don't know if you guys have ever used that free Slicer app from Autodesk. Revit's sort of like building information modeling. It's really kind of difficult to do anything outside the box with it sometimes. But Autodesk has a series of other tools that can work back and forth with these things, right? So here you see like a sort of three-dimensional volume, but it's been waffled, right? In other words, you see it's sort of two-way system filling the volume with cardboard. And basically that's just using the contouring tool on a solid, right, to generate these sort of parts that can then be laser cut, nested within sheets, labeled, laser cut, and then notched, and then put back together. So very similar, actually, to what you guys are doing for your structural ribs, right, for your shell, your grid shell prototype. Same with skin components, right? I can take a surface and break it down into quads, of course, but if I break it into triangles, each triangle can be laid out flat. From there, it's simply a matter of adding tabs, right? Making sure that there's labels, and then it's all about, you know, how you put them back together, right? So again, we're always trying to think about, you know, that detail as well, that sort of architecture has always been about sort of details, right? From a long time ago. Of course, a very famous modernist architect from Germany, Mies van der Rohe, talked about, you know, God is in the details, right? And so, you know, always looking at sort of how these things go together really nicely and anticipating things like the materials, how they work, or how they work together, or how they don't work together. Material thickness is a big thing when we're talking about making models and using the laser cutter as well. So let's talk a little bit about some of these strategies with that introduction in mind. So one way to think about taking a complex shape is by sort of slicing and dicing or contouring it, right? And we've been, again, doing this for a long time, millennia. As human beings, you know, taking very complex shapes based off of, you know, geometry that's complex and based off of performance, like let's say making something aerodynamic, like the hull of a ship, right? This is basically boat building 101, where you take something incredibly complex and then you slice it and dice it so you can find all of the shapes of these two-dimensional ribs, right? The structural ribs for the boat hull. And we can do something similar, right? This is an interesting example done by a Swiss firm. What they did is they were setting up for an exhibit of their work in a gallery space in probably Zurich, because, you know, it's Switzerland, of course. But what's interesting here is that what they did is they took a landscape and they sliced and diced it, they contoured it. And then each of those slices, each of those sections could then just be sort of planar fabricated with a CNC router, right? And so you see here the three-dimensional model, right? They vary the spacing. So sometimes the ribs are sort of alternating. So there's a rib and then a space, and a rib and a space. Sometimes they filled it in so that it becomes a solid, right? In this case, they're actually using and sculpting some of the faces so that you would actually get a nice smooth surface. So instead of trying to like leave the steps in, they were trying to sort of adjust this out. And then this became a sort of substrate to display a set of models and things like that they were putting on display. Now this is at the gallery scale. This is sort of scale of furniture and exhibit scale. We've also seen this at skyscraper scale. So this is an example. This is called the Aqua Tower in Chicago. It's done by Jeannie Gang. If you don't know who Jeannie Gang is, you should look her up immediately. She's probably one of the badass women architects in the whole universe at the moment. And what's interesting about this project is what they did. So they took a three-dimensional object you know, they sort of highly sculpted the outside, thinking about these balconies and these units. But the whole idea is that this is in the Loop in Chicago. The whole idea was about maximizing different viewing angles, right, from different portions of the for each unit. Sorry, so to say. So, you know, from the south, they might get certain views. From the north, they might get certain views from the east and west, right? And so, accordingly, each slab, each floor plate, is slightly different than the next. It's a pretty interesting project, actually. I had better diagrams of how they did this, but it's suffice to say, you know, this was just a NURB surface, right? That was adjusted, and then what they did is they just contoured it in the Z direction, okay, to slice and dice it to get those each section at each floor, and then you just extrude those down whatever the slab thickness is, and boom, it's done, right? Anyway, it's really important when you're on Lake Michigan, in the middle of downtown Chicago, to maximize your views, right? What's interesting is that then you can start charging a lot for each unit rather than just the units that are pointed at the lake or pointed at the Hancock Tower, or, you know, whatever. Taking, again, another three-dimensional object and sort of contouring it, right? This is one strategy for thinking about complex shapes. And of course, you've probably done this numerous times in second year with terrain, right? Again, complex shapes like landscapes lend themselves to how do you describe these things two-dimensionally, and then how do you build them three-dimensionally in model scale, right? This is similar to a pancake model for, let's say, a landscape, right? For your sites, things like that. So you guys already have practice with this, I'm sure, no doubt, I hope. This was something that was put together and then assembled, put in a gallery space. Okay. Another way of thinking about this, and this is highly dependent on the geometry that you're working with, but rather than sort of slicing and dicing into sections and then, you know, cutting those sections out and then putting them back together and laminating them into a solid, another way of thinking about this is unrolling or unfolding the geometry, right? And this is again, a practice, the geometric practice that humans have been looking at for a long, long time. And it's not lost on you, I hope, from this graphic that some of the first people to sort of look at this problem are cartographers, looking at the doubly curved surface of the Earth and trying to figure out how to lay it out flat in order to make maps with minimizing or maximizing distortions in particular ways, right? And so you start to see the different sorts of ways that cartographers actually try to unroll our globe. And then again, this is color coded based off of the amount of distortion, right? So yellow, least amount of distortion; green, medium amount of distortion; orange, maximum amount of distortion. Suffice to say, when things are doubly curved, it's hard to actually unroll them flat without bending or stretching, right? Distorting, or ripping, tearing, and actually making, like you can see down here, a bunch of incisions, right? Again, you're always still approximating the double curvature when you're looking at a flat piece of paper or something, and then trying to roll it back up into something doubly curved, right? But this idea that, you know, singly curved items can actually be easily unrolled, right? And then anything that's folded can be unfolded, I think is really important. You can see some examples here where this is from the Architectural Association in London, really good architectural school, internationally renowned. But in this particular studio, they're looking at the material generating the geometry, and then the geometries, then seeing how complex they can get with the geometries, right? And so starting with, let's say, a strip of, oh, I don't know why that moved backwards here. Starting with a strip of steel and then bending it, right? They can begin to generate a lot of different geometries, both curved and twisted. And then simply starting with the material, right? And with that logic that it starts as a flat piece of material, they can generate lots of different complex pieces in complex systems, but guaranteeing that each piece can then be re-unrolled or flattened out into a flat piece again. So they take this, they do a bunch of physical mock-ups, they take what they learn, they start to generate things computationally based off the material logic, similar to sort of the things that you saw with Akim Menges in that video. But then they were able to generate lots of different complex things computationally, but generated off the logic of the material, right? So the geometric logic of the material in this case being that everything was done so that it could be flattened back out and just basically fabricated with planar laser cutters or water jet cutters, right? Same thing here with paper strips, right? Lots of different ways you can generate just singly curved, sort of approximately double curvature and really strange geometries with singly curved components deployed in the system, okay? Hexagons, polygons, rolling, unfolding, right? And the same stuff that we typically see from Frank Gehry's office, right? So Frank Gehry has this remarkably odd formal vocabulary, right, of curvature, right? But oftentimes, what you see, if you ever go to his office, sorry, I want to try to drink this coffee before it gets cold. I hate cold coffee. Ugh. In fact, I think the worst thing in the world, the most demented thing ever is iced coffee. Ugh. Anyway, sorry, just want to try to drink some of it while it's still warm. But anyway, what you see is that, you know, it's actually tremendously materially driven practice. They make lots of stuff. It's a very tactile practice. And oftentimes, this aesthetic of the curvature, what it looks like, you'll notice that it looks like strips of paper or strips of metal, right, that have been curved in several different ways and then put back together into some sort of three-dimensional thing. And that's no coincidence. In fact, it's a feature, not a bug, in that they're always looking for ways to make these things. And so if you can think about sheet material that starts flat and then basically make a series of transformations to it physically, then once you scan that into the computer, right, you could theoretically unroll everything out and flatten back out again. And that has profound implications when it comes to the ease of production and then how much it costs, right? So what you'll often see are these sorts of diagrams. Oh, I'm not sure why this thing keeps skipping on me. Oh, I think my mouse is just really jumpy here. I'll try to use my touchpad. What you'll see is these false color Gaussian curvature analysis maps, okay, where they start to analyze the curvature of the surface. And so you start to see these colors being put out. And so what you'll notice is that, like, let's say the blue, for instance, probably means singly curved. It only costs $5 per square foot to make. The yellow is doubly curved, but not too within a certain range or tolerance. So it only costs $15 per square foot to make. And then the red are the problem areas. You could make it, but it's going to be really cost prohibitive, right? So it might cost $800 per square foot to make, right? And, you know, because you have to make your own custom dies and then stamp the darn thing into place or something like that, right? So for each individual one, and you know, each one's different and over the course of the skin of a building, etc. Right? And so what you see is that they're always playing a game between the geometry and then the series of panels, how they panelize it into smaller components and how those components are made. And again, how they can be put together and all that sort of stuff. So what you'll see is a lot of different tricks to this, right? Unfolding is another way of thinking about this, where you take something that was round, like a globe. Here's another way of thinking about this. Instead of thinking about curved sheets of paper, you think about flat planar triangles, right? And so you triangulate and basically turn or approximate something that was curved into something that's made of entirely planar facets, right? And it's all about how you unfold them and then put them back together, right? I mean, I think we've all probably at some point in time had some sort of weird paper construct that we had to make. You know, I always think about, like, you know, when somebody would travel and they'd bring me back something from a museum store or something, and there was always these sorts of things, these sort of weird things that I had to do. Here's another example. And in fact, this is from the same buddy of mine, Andrew Cutlass, who gave us our rhino script that you're using to generate the grid shell ribs. He actually generated a number of prototypes back in grad school at the AA, these hexagonal honeycomb prototypes using the same logic, right? And so the idea is that, let me just get my, if I can get my annotate tools on. The idea is if you took a sheet of paper and just folded it like this, a strip, And then you got another piece of paper and strip and fold it like this. And you put them together right here and right here, you start to make a set of honeycombs, a set of hexagons. And then if you do that, oh, I don't know why that disappeared. And it's a clear underline. There we go. Oh, and apparently someone's trying to chat at me, but I can't see that. Oh, come on. Where's the chat box? That worked. Oh, okay. That must be pretty old. Here, let me just move on. Right. So you can actually begin to take a surface and break it down into a series of hexagons, right? Each of those can be flattened out. Each of these rows, I'll just bring up the annotate tools are not the most useful things here. Each of these just start as a strip of laser cut stuff that's then folded and then assembled, right? And so you have that strip, and then you have this strip, right? And on and on and on. So it's actually a pretty simple system, simple set of ingredients when put together actually creates pretty complex. What is it? Sorry, I apologize for this moving around. And for some reason I'm not sure why this keyboard isn't working. There we go. Really complex sort of effect, right? And here's the idea, right? You take this larger surface, you panelize it, you take each one. These are all those different strips, right? It's really simple to laser cut, right? Here's what they look like when they're put into, whatever size of material that this bed of the laser cutter wanted to use, right? And then you just put them together, strip by strip. Another way of thinking about this is by taking something larger, doubly curved, and trying to figure out how to break it down or panelize it into a set of shapes. This practice is called tessellation in mathematics, right? Where you sort of understand how you can pack together various shapes and sometimes repeating, sometimes non-repeating patterns. Here's an interesting example from Melbourne, Australia. It's called Federation Square. In Sydney, they have the Opera House, and, you see it every New Year's, right? They have the fireworks over the Opera House when they celebrate the New Year. And of course, they're celebrating the New Year like 23 hours ahead of us or whatever. But in Melbourne, they have this, right? This is called Federation Square. It's the large sort of gathering space and civic pride space in Melbourne. It's relatively new. What's interesting is it looks like this sort of chaotic sort of this actually looks kind of like your Project Wands, doesn't it? Like all of these struts and like a space frame sort of thing. Anyway, but it's actually created from one or two very simple shapes. So what they did is they had a material palette of, let's say, zinc panels, glass panels, and stone panels. And they found this sort of shared common size for each of these panels in metric. So I don't know what they are in millimeters, but it looks like it's 3,119, whatever. So 3.119 meters or something by 2 meters or whatever. But what they did is they figured out a way to sort of break these down into identical triangular shapes, and then figured out different ways to recombine these triangles. Right. So first of all, you start with a standard size of material, and you break it down into triangles, right, without any offcuts or waste or scrap. And then it's about how do you recombine the triangles into a bunch of unique shapes, right? And then how those can be tiled, right, or tessellated across a surface, right? In this case, looking at elevation studies, right, and then how that becomes three-dimensional to create structure as well, creating these sort of brilliant effects with light, both during the daytime when the sun projects shadows into the inside, and at evening time when things are lit up and glow on the outside, right? You see this in a number of different ways, right? So, but again, I would consider maybe triangulation a different way. Like you see here, this is Norman Foster's courtyard over the British Museum. So this was an outdoor courtyard. He enclosed it with glass. What's interesting is that if you see this is really pixelated. The graphics here are really, really small, unfortunately. This is the plan. And so you can see that there is a neoclassical outline to this outdoor courtyard and a neoclassical circular structure on the inside, it looks like it would be like completely symmetrical. But in reality, you know, maybe it was designed symmetrically, but in reality, the physical reality, when they scanned the space with a with a laser scanner, they found that actually everything was way off. And so each of these triangles actually turned out to be completely unique. And so what's interesting is that they went for, what is going on here? Why does this keep changing? Sorry, I'm trying to do this in spite of my tools here. All right, so you have each of these struts, and they actually all combine into these sort of asterisk connectors at each node. And so these asterisks are all also each different. Some of them are highly unique. Others are, even the ones that are right next to each other are slightly different. And so those all had to be generated parametrically, and then they were fed to a water jet cutter. And so you can see these are actually quite deep. With a water jet cutter, it works similar to a laser cutter, except you can cut through things like titanium, and you can cut through like 10 inches deep of titanium, all through like funneling water with some aggregate at super high velocities. So interestingly, water jet cutters are used primarily in the aerospace industry. And one of my favorite things about these is that, like some of the more powerful ones, if you turned it sideways and shot a water jet cutter laterally, it would go like something like 3 football fields before the stream actually arced due to gravity, because it's that powerful, right? So it's used to cut through extremely hard materials. Anyway. Oh, actually, I guess this was plasma cut. Look, because you can see the torch right there. Yeah, my bad. But water jet cutters are pretty cool. I think I have some YouTube videos of them somewhere. Maybe I'll try to show them. Right? Even things like Bilbao in Spain, Frank Gehry's masterpiece, the Guggenheim in Bilbao, or this bank company headquarters that he did in Berlin. You know, you can see these very complex shapes, but then they're post-rationalized into triangles. What's interesting here is that you see a rectangular facade. Rectangles aren't necessarily planar, but as soon as you cut them with the diagonal, right, you have 2 planar triangles, right? Now there's always 2 sides to a coin. And so what's interesting is this is a Norman Foster project, the Gherkin in London. What you'll notice here is that each component, instead of being triangles, are diamonds. And what's interesting is that what they figured out is that if you look at certain types of geometries like toroids, like torus, you know what a torus is in geometry? It's like a donut. It's like a circle swept around a circle. It quite literally looks like a donut. So if you use those sorts of patches and use those sorts of geometries, and this isn't a torus, but what they were doing is they were using a similar, a different piece of geometry that also produces planar quads, right? So if you can make quads that are planar, right, and you don't have to break them down into smaller triangles, then you've basically, you know, cut the amount of on-site labor, right, the amount of details and connections and joints in half at least, right? And that also adds up in cost, right? So on-site labor is, you know, a remarkable cost actually, right? Here's another thing. This is just a rain screen in Prague. This was by Frank Gehry. This is the dance hall actually. This is nicknamed the Fred and Ginger building. One is, for better or worse, you know, one is, it looks like 2 figures sort of dancing according to Frank Gehry, right? And I guess the glass one's supposed to be more feminine, the stone one is supposed to be more masculine. I don't know, whatever. But this idea that, oh wait, sorry, skipped ahead. You know, taking these quads and actually then offsetting them and then actually overlapping them almost like shingles, right? Underneath this then is the actual skin. This is more of just a rain screen. So there are a number of different ways you can think about these skin components and how they interact. Are they flush with each other? Are they all self-contained within their own cells? They overlap. Speaking of museum stores, this was always my favorite thing to do when I was little, was to take these model kits and assemble them, right? Interlocking assemblies, that's something that we're doing right now with the notching, right? You know, interestingly, these sorts of things were probably some of the first things that were done with a laser cutter by hobbyists, right? Making, let's say, dinosaur skeletons and things like that that can be assembled. Let's see here. But there are other ways of thinking about this. This is, I don't know if you guys ever looked at PS1 in New York. It's the first public school in the New York area. It's in Queens. But it was bought by MoMA, and it's now a gallery, like a sort of satellite gallery of MoMA. It's in Queens. Every year, they have a courtyard in front of the school, and they invite an architect, young architect, to do an installation that facilitates, let's say, like a whole summer full of like Friday evening parties and galas. So this is one that that was put on maybe in the second or third year. But you can see these sort of steel, rusty steel ribs spanned with this PVC pipe that almost looks like isoforms of a surface. I don't really care for this so much. What I find interesting is that if you think about these ribs, just look at these ribs for a minute and try nesting them into a sheet. That'd be really inefficient. You have a bunch of weird offcuts, right? And so what he did is he broke these up so that, let's see here, let me just pull up my annotation tools here, right? So if you think about a sheet of, let's say, steel, and then one of these ribs takes like the whole thing, right? Maybe you get a few of these on here, right? But then the next one doesn't even fit, right? You're gonna have a bunch of weird offcuts. And so you're wasting a lot of money. And so what he did is for each of these ribs, he broke them up into smaller pieces, right? And so those could actually be nested much more efficiently on a sheet of material, right? So that you're maximizing the amount of yield, the amount of material you're getting for each sheet, right? Breaking it up into smaller and smaller components, right? They can then start to be arranged and nested into different places. But then comes the interesting geometric jigsaw puzzle, putting it back together. In this case, right, each one had a unique jigsaw puzzle joint that also had flat parts, and in fact had, I think, some engraving showing where the welders should put the welds, right? This is all done very quickly. Those aren't the most beautiful welds in the world, but they are what they are, right? Okay, and so thinking about these sort of interlocking means of doing these things, the same architect, Bill Massey, when he was doing these sort of custom houses, what he would do is he would make the concrete formwork, you would CNC routed out of foam. But then the foam pieces would actually have these puzzle piece, interlocking puzzle piece joints. Sorry. Where's my cursor is? Where is it? Hopefully my computer isn't frozen up. Oh, I know what the problem is. Where's my mouse? Oh. For some reason I can't see my cursor. I have a feeling it has everything to do with these annotation tools. Oh, help, help. There we go. Clear. Clear all drawings. I can't actually see my cursor. I'm just doing this by blindly. There we go. Okay, now I can see my cursor. I don't know why I went backwards, but okay, so as you can see, the formwork was actually, had these puzzle piece joints, you know, so these things were actually, the formwork was actually, what was I talking about? Oh, styrofoam that was CNC routed really quickly. Then they were put together these puzzle piece joints, and then those joints were actually left as impressions inside the concrete that was casted, sort of an expression of how the material was cast in a sort of gorgeous way. Okay. I'll just sort of skip through this. I don't want to take too long, but I think you guys probably recognize this, right? Right. So taking a surface and then cutting it two ways, right? And then giving the labels, spraying out all the ribs, adding all the notches. Okay. This is what we're going to be doing next, is actually, you know, putting some components and then laying them out, and we'll use Grasshopper for that. Okay. Really quickly, just one more thing as you're talking about laser cutting, right? This idea of nesting, thinking through this process of taking a bunch of components and figuring out the most efficient way to sort of lay them out in the sheet so that we're minimizing the amount of waste. Or if you have waste left over, like in this case, you get like 3/4 of a sheet and it's still a rectangle, so it's actually a pretty useful offcut, right? The idea of assembly instructions, right? So oftentimes what you'll find is that plan section elevation does not work for, let's say, these grid shells that we're going to be putting together. But really, sort of three-dimensional instructions like this will be the key to actually sort of understanding which piece goes with what and which slot matches up with which, tab or whatever it is, okay? These are examples from shop architects in Manhattan. This was a park structure that they did in Greenport, Long Island. And the whole thing was digitally fabricated. And the CDs, the construction documents, didn't really have any like plans and elevations. It was all a bunch of like axons and showing like how things actually were put together piece by piece. Okay. Just like this, right, which starts to resemble, like some of those automobile kits, model kits I used to use when I was little. Like you snap everything off and you'd you'd prime them, paint them, and then start to glue them together. Those came with instruction manuals, right? That sort of looked like this, where it shows how sort of the three-dimensional version exploded and pulled apart, right? This is actually a set of custom casework that shop architects did for, I think it was Virgin Airlines first class lounge in JFK Airport. So that's what it looked like. All these pieces put together as sort of dividing walls / casework / table bases / seating. They're both part screen and part projection, right? So it's pretty interesting. So anyway, with that, I'm just going to end that. But I just wanted to I'll end the sort of lecture. I just wanted to sort of throw that at you guys. There's a lot of different things that are happening, out there that you should be aware of. And again, look up, folks like Jeannie Gang and shop architects. So here we go. I've included this graph that I'm going to show you right here on Canvas at the bottom for today. Okay. And so I just wanted to show you what we're going to be doing, though. This is not too dissimilar from what you guys are using, but this is like a doubly curved saddle shape. It's a different surface than what you guys are using, but I'm just going to use this as a demonstration. And what I have here is a graph that asks for one surface as its ingredient. And it takes that surface and it breaks it up into a bunch of subsurfaces, right? It finds each of these vertices and if I just look at this really quickly, each one, it finds each vertice for each of these quads, right? It breaks up into a series of quads, find each vertex. There should be 4 vertices per quad, right? That's by definition, right? 4 sides, 4 vertex, 1 face, right? And then it also, interestingly, evaluates the surface at a UV parameter, which of course I can change that UV parameter and open these or close these up more. Okay. Plots a point at that location on each checker, right? Draws a line in the normal direction off of it, finds the endpoint of that line, right? And then it begins to connect the dots with triangular components, right? So here's a triangular surface, set of triangular surfaces. Connect the dots, dot, 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 and then this set as well, dot, dot, dot. Then what I do is I take each of those and I join them, right? So this gets joined to this and this gets joined to this, right? So if this is 15 by 15, I should have 225 cells. So I have 225 joined poly surfaces or B-reps. And then I feed it into this unroll widget. Grasshopper right out of the box doesn't have an unroll widget, right? Which unrolls or unfolds things. What you'll need to do is download the Lunchbox tools, okay? Install them, and then you'll have a set of a new tab called Lunchbox, and part of the tools that installs is an unrolled B-rep. So that actually lays these things out on the XY plane. Okay. Meanwhile, down here, I've created a grid of points. And I use that grid of points to then take each of these unrolled components and lay them out in that grid, right? Like move each one to each point in a grid, right? Otherwise, look, when it unrolls them, sorry, hold on. Let me just turn on the preview for the unroll. The unroll unrolls them all at the same point, 0, 0. So now what I do is I move each one serially to a point on the grid to sort of spread them out. Yeah. And on top of that, I then give them some sort of text label. So the first one would be 1, 1, and then the second one would be 1, 2, 1, 3, 1, 4. And then the second row, 2, 1, 2, 2, 2, 3, 2, 4, right? This is like Battleship, except instead of like C4, it's like 1, 1. I didn't want to deal with letters. Okay. These are just a few steps away from being exploded, where you just find the edges. Let me just do that. Right? Just get the edges. And in fact, I've even exploded them so that we can get the outside edges, right? Those would be the through cuts, and put those, bake those on a particular layer. And then just this little score line, right? Which I could put in a different layer, the score layer, right? The blue layer. And so that way I'm just cutting out one shape and then I'm making the score so that I can just fold it rather than having two pieces that I have to like figure out where they go and try to glue them together, right? So there are different ways you could think about, or logics you can think about with this stuff, okay? At the same time, I'm making a set of text labels. I just mentioned that, yeah. So 115. So we have 1, 1 in one corner all the way to 15, 15 in the other corner. Yeah, right. So it's just generating a list of numbers, cross-referencing them against each other, and then using a text tag thing that I can bake and then explode in Rhino. Again, with a friendly reminder, you need to come up with your own unique design for a shading component. Do not use this very simple one that I have provided. And of course, I somehow managed to misspell simple. Come on, Josh. Okay. What's interesting, though, again, everything moves from left to right. So as soon as I change this, right, I can change the location and change fundamentally the geometry of these things. I can also change, I just sort of look at this a little closer. Oh, maybe. Not sure why this is. Sorry, let me just enter my rotation here. I can also change how deep or shallow these things are, what size they, which side they even project out from. Here, let me just do that. Right, so the height, right, to make this more or less spiky. But what's interesting is that not only do I see the three-dimensional version changing in real time, right, but all the fabrication information changes in real time as well, because everything goes from left to right. So as soon as I start to change this stuff, right, you can see all the components that are laid out flat move in real time. Right? Everything updates. Everything gets unrolled and laid out, right? Now, if I get too spiky and the components get too big, then I need to change the spacing for how they're laid out, right? So they don't overlap. It'd be tragic if I started to laser cut into other pieces, right? So, you know, maybe I do that to make sure that they don't overlap. It's like magic, right? Oh, okay. So let's start out simply. And I'm going to start a demonstration today, and we're going to keep doing it on Wednesday, okay? But what I expect you to do is look at this example between now and Wednesday, okay? Watch that 21, the video labeled 21, labeling, laying out, flattening, unrolling, okay? So that you sort of understand where we're going to go, okay? And in the meantime, design. Just get a piece of paper and a pen or pencil and draw. I highly recommend starting with a sketch, right? So let's start with a new document. Just blow all that stuff up. It's not. It's easily made again. All right. I have a surface in Rhino. I need to bring it into Grasshopper. What do I do? Try not to type it in the chat because I can't even check that. Oh, there's 14 chats. Oh, dear God. Oh, yeah. Okay, CNC, the dance house, yes. Huge waterfall in the middle. The waterfall one, right? Oh, the Shanghai. Yeah, okay. You guys are, wow, okay. So you guys are, interesting discussion here. So anyway, yeah, I would CNC a system called Router Sim. We had the CNC things programming those parts for us and whatnot. Yeah, nesting is a difficult thing, right? So to get a truth-shaped nesting program, they're not cheap because it's a hard thing to do. So they don't give them away for free. What I would what I would advise is that you just do it manually for now. Okay, there are softwares that will do truth-shaped nesting for all the unique components that we have, but they're a pain in the ass. And depending on how much leeway you want to give them with how many times they can rotate them around, it can take lots of time for them to find the most optimal nesting solution. But yeah, I mean, if you have access to it, then go for it. But otherwise, I'm not gonna make you pay like $800 for a cheap one because they are not cheap. Good question. Anyway, back to this really quickly. I want to get through some of this. Yep, surface widget and the params, right? I'm going to go to the params tab, go to geometry. All of these are placeholders where I can reference something in from Rhino into Grasshopper. Right? So in this case, yep, I think Christian, you said it, surface widget, right? And once I place that, I can right-click on it, set one surface. Grasshopper disappears. I can go ahead and select the surface in Grasshopper or in Rhino, and now it shows up as this sort of red, green if I select it preview, right? All right. This is a quick recap of some of the stuff you've done with surfaces so far, but I'm going to go ahead and divide this surface. If you think about it like a spreadsheet, right? Spreadsheet has rows and columns, right? And so it has a bunch of cells, and that's exactly what I'm going to do here. I'm going to divide it with latitude lines and longitude lines in order to get quad-shaped cells, okay, in a grid. Now, obviously, the grid is in like a sort of rubbery, doubly curved sheet of surface, but instead of a flat planar one, like our computer screen. Let's see. So I'm going to go to Surface Tools. I'm going to go to Utilities. I'm going to find isotrim. And what it wants here is the domain, right? A two-dimensional domain. Okay. And I'm just going to go ahead and plug this surface in. I'm going to right-click and say reparameterize. What the reparameterize does, remember, is it takes a sort of really specific U and V max limit and changes it, the minimum maximum to U and for U and V to both 0 to 1, right? So instead of being 0 to 15.96, blah, 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 or whatever this thing might be, right? Now we just can deal with the absolute 0 to 1, 0 to 1 in both directions. Okay, so I'm just going to reparameterize. It's a good habit to get into with both your curves and your surfaces. Domain of subset. So this is a really interesting tool. I'll just really quickly, again, recap here. I can give it a two-dimensional domain. And what that means is that it's going to, you're going to give it a domain in the U, sorry, a minimum maximum in the U and a minimum maximum in the V in order to demarcate the sort of quad-like shape, right? So for instance, if I, let's say, made 4 number sliders. Here, and plug them in here. And let's say I'm going to go between 0.25 and 0.5, 0.5 and 0.75 in the other direction, right? What I'm doing basically is giving it a minimum latitude, minimum longitude, maximum longitude, right? And then it's finding that parcel bounded by those 4 sort of streets, right? Does that make sense? And so, of course, if I change this, then I get more or less of that surface, right? Now, what I'm going to do is I'm going to generate a list of these in order to generate a list of patches, right? A list of sort of subsurfaces. Okay. So what I'm going to do is I'm going to create a two-dimensional domain, and I'm going to divide it in number of times in both directions, just like if we were dividing a surface. So let's see here, math, domain. I'm going to construct a two-dimensional domain. Yeah, I should probably do that. Deconstruct, divide a two-dimensional domain. Right, okay, here we go. So here's how I can determine how to divide a two-dimensional domain. I need a two-dimensional domain, so I need to create one. That would help. Whenever I'm in doubt, I hold my cursor over the ingredients or the outputs to understand what it either needs to work or what it's going to spit out at me once it works, right? Okay, so the base domain. So I need just a two-dimensional domain to divide. All right. So I'm going to do that. I'm reparameterizing this to 0, 1, 0, and 1. So I just need to make a 0, 1, 0, 1 construct two-dimensional domain. This is 0 by default, 0 to 1, 0 to 1. Yep. So go ahead and plug that in. The number of divisions, I think by default is set to 10 each, but that can be a set of variables. I'm going to go ahead and make a number slider. I'm going to constrain it to integers. So I just use whole numbers. I'm going to change the minimum to 1 because it doesn't make sense to divide something 0 times. And I'll make the max something really ridiculously large, like 30. Okay, and I'll go ahead and copy and paste that. So I have two of them, one for U direction and one for the V direction. Now at this point, I'm going to go ahead and turn the preview off of this one so I can try to see this. So let's plug this in. All right. And I'm also going to take that original surface. I'm just going to hide it for a minute. So we can see basically these divisions as I start to change these things. Right, so let's go with 10 in this direction, maybe 20 in this direction. Why not? No, maybe 15 in this direction. 12. No, yeah. I'm so indecisive, it's silly. Anyway. Okay. So what's interesting now is that I have 240 sort of checkers in this checkerboard, right? So what it does is it says, oh, so you want to generate a surface between, in the U, 0 to 0.05, and then the V, 0 to 0.08333. And it portions that parcel and the map off, right? It says, okay, this is now its own little surface. And it does that 240 times, because what we've done is we've divided 0 to 1 20 times, and 0 to 1 12 times. So 12 times 20 is 240, right? So we should have 240 two-dimensional domains, defining 240 checkers in the checkerboard, right? So in other words, we have 12 in one direction, 12 rows, and 20 columns. Right? Just to prove my point, just so you can see that, let me just look at each of these in the list. Let's see, list length. Yep. Oh, no, not list length. I'll just pull out the first item. This will let me just show one item at a time here. That'll be interesting, right? So there's the first one. And let me just make a slider for this. Okay, so there's the second one, and the third one, and the fourth one. Here, I'll go ahead and highlight a green here, and I'll change the minimum to 0. You don't have to actually do this. I'm just trying to show you. Here we go. First, second, third, fourth, fifth, sixth, seventh, eighth, and they go in the order of the columns, right? Okay. Just as an aside, okay? Okay. And so now what I've done is I've broken up this large surface into a series of smaller quads, right? I've panelized it into a series of, tessellated it into a series of four-sided shapes, four-sided surfaces. I can take each of these surfaces, and in this case, what I'm going to do is I'm going to deconstruct them, or basically explode. Okay, I'm going to explode them, and so I'll get all of the faces. There's only one face per surface, right? It's just the face of the surface. I'll get all the edges, and I'll get all the vertices. Now, what's interesting is that for each of these quads, I have 4 edges, right? And for each of these quads, I also have 4 vertices. And so what you'll notice is that as soon as I do this explode sort of brep deconstruct widget, what I get out are data trees, right? And the way to read this, let me just pull up a notepad so you can see these things. Okay. Here we are. You have 0, 0, 0, 0, 0, 1. I'm looking at the left-hand column in that yellow pop-up, right? 0, 0, 2, 0, 0, 3, 0, semicolon, 0, semicolon 4, all the way to 239, okay? There's 240 branches of this data tree, right? Corresponding to each quad. And then inside of each of those branches are the 4 vertices for each of those quads, right? So for instance, the first quad has 4 vertices, right? Here they are. This is the first branch. So first quad, 0, 0, 0, has the first vertex, second vertex, third vertex, fourth vertex. Then it moves on to the next quad, right? The next surface that it exploded. Here are the 4 vertices for it. Same, 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 all the way down. There's 240 of them, right? Okay. Same with the edges, right? There's 4 curves on each of these. Okay. What I can do is I can start pulling these out. So I can pull out, let's say, the first from each of these lists. Here, let me just pull this back out. I don't know why I got rid of that. I think that was actually a pretty helpful way of seeing this. So let's say I just want the vertex 1 of each of these quads. Has an index of 0, this one, and this one, and this one, and this one, right? I'll go ahead and do that right now. I'll make a diagrid. I'll make a series of X's just so you guys can see what I'm up to. This will be the last thing I do today, okay? I'm going to go ahead and take, what I see here is I have a set of tree branches, and each side, each one has like 4 items in each, right? Basically, I have a list of a list of 4 items, right? So list of lists. I can take the first item out of each of these lists, right? By using this int item widget. Yeah, list item. So I'll feed in this data tree, basically a list of these lists of vertices, right? And I'm going to set the integer to 0. Right, and that'll give me just the first item from each. Right, so let's go ahead and look at what it's spitting out. I find it's really helpful to just sort of compare these two things. Right, and so the first item from this one, negative 25.43, that's it right here. And then the first item from this one, negative 2, that's this one, all the way down to, oh, sorry, I don't know why that didn't. I was trying to scroll, didn't work. Ay, ay, ay. Let me just change that. Here we go. I'll scroll all the way down. All the way down the end, right? This last one, right? 0.59, blah, negative 16, negative 15, right? So what we're doing is we're just pulling the first item, let's say the vertex 1 from each of these quads. Okay. And let's pull out the second one and the third one and the fourth one, right? And separate them all out in their own widgets here. So I'm going to go back to sets, find the nth, right? I'll go ahead and plug in this list. In this case, I'll give it an index of 1, which gives us the second item in each of those lists. Oh, I said 1, but I typed in 2. That was strange. Okay, that'll give us another set. Go ahead and copy and paste that. I'll just change the index item number here. For the third, I'll give it an index of 2. Computers start counting at 0, so the first one has an index of 0. The second one has an index of 1. It's really annoying. Last but not least, I'll set this one to get the fourth vertex to an index of 3. Okay. Now, what I'm going to do is I want to take the first vertex and connect it to the third vertex to create a diagonal across the surface, and a second to the fourth to create an X across the surface, right? 2 diagonals, X marks the spot. All right, so I have a list of points here and a list of points here and a list of points here and a list of points here. I'll just make a line widget and I'll connect first and the third alternating vertices. And then I'll connect the other set of alternating vertices, the second and the fourth. And now I have a sort of diagrid pattern. Ta-da, right? Just by simply connecting the dots. Okay. So this is essentially, excuse me. Ooh, my throat is dry. I should have been drinking more of this chai. Anyway, these are the first steps that I want you guys to make sure you understand, right? Taking the surface, break it down into smaller surfaces, exploding those smaller surfaces so you get the vertices and the edges, because those points and lines will start to build components off of them. And as we build it off of one, it'll build it across the whole list of cells, okay? That's really important, because if you're gonna do this, you're gonna build 240 of them, I want you to just really build one, and the 240 of them appear. Not that you have to like manually model each unique component. There's 240 of them, okay? So I just wanna make that very clear, right? This is again, recounted in video 20, which I've added here for your reference. Today's lecture will be posted right in here, okay? For your reference, again. So please, 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 look, this is exactly what we just did, right? Dividing and populating a surface, okay? We'll continue this on Wednesday, okay? In fact, I'll probably just do this quicker in front of you, and then we'll move on from there. Except instead of building a diagrid, we'll build this sort of half pyramid shading system, kind of lame, that I'm using for this example for you guys. I'm building a lame one, so I'm not taking a cool one that, you know, one of you might stumble upon, right? That way you guys have, you know, more options at your disposal, right? It all starts though with doing a sketch. Oh gosh, well, that was gonna work out really well. I'm holding up a piece of paper with a sketch on it. Yeah, there we go. Okay. So that's where I would start if I were you guys. There's got to be a ton of questions in your head. So what in the world is going on here? Is it clear where we're going, even if all the little details aren't quite there yet? Having problems running fitting your parts in the 18 by 32. Yes. Oh, I was going to address that too.
Yes, I also have the same issue. I don't know, it's scaled differently, even though I used your script.
Let's say I'm gonna start a new file. I'll say large objects millimeters. I don't know what it is. Okay, so I'm gonna go to File, Open, and open up the surface classification file I gave you guys, right? Which
we can see nothing.
Let's see. Oh yeah, sorry. I didn't share my screen again. All right, you guys see it now?
Yep.
Okay, cool. So I have a new file going. I'm going to go to File, and I'm going to open up this surface shell classifications, right? Before I bake these things in, right, I want to make sure I've set my units. So I go in Rhino to Tools, Options. Tools, pull down, Options. Do you guys get that? Tools, pull down, Options. Brings up a box. Along the left-hand side of the box, there's a number of different categories for options. Units is the one I'm going to look for. And I'm going to set model units to inches. Not feet, inches. There we go. Hit OK. Now I can go ahead and bake these surfaces and they'll be the right scale and the right units. Okay. So you want to make sure that you have your unit set to inches in Rhino before you bake one or both of these in. Okay. Then from there you can run the Rhino script. All right.
All right, Josh, it's Antonor. I think I'm having, because I don't have the Rhino script, so you baked it for me. So everything, it's already there on the scale. I think that's where I'm moving.
Which one were you using? The double, this one or the other one?
I'm using the dome.
The dome.
Yeah.
Bake. Okay, and then what were your parameters?
1.2, 20 by 20, I think.
Let's see here. Hold on, let me bring up this. Okay, sorry. 20 and 20?
Yeah.
The height was 1.2,
Yeah.
right? I'll just pick, okay, and then the material thickness was 060?
Yeah.
Yeah. And then for reference, in top view, I'll just give this file to you here in a minute. But for reference, right, let's see, 32, 18, 32, close. Let me turn off this silly grid here. Can't see anything with this. Right, so this grid, this box is 18 by 32 inches. So your components should easily be contained. You shouldn't have any components that are larger than can be contained. Right?
Okay.
Now you might need more than 118 by 32. I don't know, but you won't have a component that's too large.
Oh, that was my question. Okay, so it's not gonna fit all in one sheet.
Oh, I don't know. Maybe it will, maybe it won't. I don't know. That's up to you and how well you nest them and stuff.
Okay.
But the idea is that each piece can fit within the laser cutter bed.
Okay, that's what I wasn't sure because I didn't know
Okay. So do you need me to send this to you or no?
No, I
Oh,
already.
okay. Okay, got it.
What is
Antonor
this?
is using the Mac version, so he can't run the Rhino script. So he was playing around and doing it in Grasshopper, and then I generated this for him last minute in Rhino script for him. Just quickly did it according to the parameters he needed. So he's not like cheating or anything. What question do you have, Maria?
So also this black grid that we have, also it's a red colors for cutting. We also need to fit this also in the sheet because those are the actual small cells, correct?
Say what?
So the black grids that gonna go, other than the scored one that we have aligned, we also need to fit those in the sheet, correct?
I'm a little confused. Are you talking about what I showed today?
Yeah, right. What you just showed right now with the script, what we already did.
Oh, okay. Oh, wait, what is this going on here? Okay. I don't know why this is doing what it's doing. I'm sorry, what are you asking?
Because when we did the script, it's unfolded all those pieces that go in the V0, V1, but those are like long strips, correct? Stripes. And together with that, it was also the actual shell that also need to be cut, correct?
I'm not exactly sure what you mean. Let me pull it up here. I don't know why Rhino is acting weird, but I'll just do this one last time here. Bake. Sure. Let's see. So I'll just generate this for you real quick, or in front of you real quick, and then I'm not exactly sure what you mean, but okay, so it's the Rhino script you're talking about, and it's generating
Yes.
this stuff. Yeah, so
You see this black thing that like the actual dome?
yeah, what about it?
So this is also need to go to the laser cutting, correct?
This is the three-dimensional version of all this shit that's laid out. Does that make sense?
Okay. So
So
basically those
for instance, I
lines.
look at this and I go, oh, so that's V0. And I go over here, oh, this is where V0 goes, right? And here's where V1 goes, V2, V3.
Got it.
Okay?
Yep.
Okay.
Okay, thank you.
Yeah, so this is a three-dimensional version. You'll be using this to generate the exploded axon.
Got it.
It'll be so exciting. Yeah.
You think it's better to copy paste those components to the laser cutting sheet or just to bring the laser cutting template to this Rhino file?
I don't know if it makes too big of a difference.
Okay.
Yeah. Just make sure you don't overwrite something.
Okay. All right.
Okay.
Thank you.
Yep. Yeah. In fact, here, if you guys actually had your shading components already designed, then you could laser cut these for your first draft as well. But you'll be doing it for your final draft. Right. Here I have them all laid out, nested inside of 18 by 32. Not nested very efficiently. I didn't have so much time here, but. All right, I'll see you guys on Wednesday. Let me know if you have any questions. You can just shoot me an email.
Thank you.
Yep, take care.